doing it from my mobile phone, and I'm doing this for the first time for your class. So can you see my screen? Is it visible so that I can start? Can anyone confirm?
Yes, sir.
Okay, okay, that's good. So we are going to start with this derivation of Lagrange's equation from DL-Emboss principle. So in the last class, few classes, we did see DL-Emboss principle, and then where we saw that we have developed an idea of generalized force. And if you consider a system, there are two kinds of forces which are acting. Okay? So the first force that we basically have is applied force, and the second force is the force due to constraint. So we're going to stick to this idea and continue with it. Okay. So this is actually the first lecture for your unit 2. So you can consider your unit 1 complete. In unit 1, partly we also studied a bit about unit 2, which is like the phase space concept that we have already seen. Okay. So the phase space concept, I think this is actually a part of unit 2. No, this is the part. Okay. So we have already done it. So it's like we are not going to go to too much detail of that. And application of Lagrange's equation, one problem we have done, which is nothing but our derivation of the equation of motion for a compound pendulum. Okay, we have done it. But we're going to continue with that. So the first thing that we're going to do today is this. So Lagrange's equation from D'Alembert's principle. Okay? And we are going to understand what is a conservative and an unconservative system, because you already know what is a conservative system, right? The work done does not depend on the initial and the final position. Okay? And we are going to use this idea to derive the Lagrange's equation. So what we are going to do is we are going to revise a bit, only one slide, whatever we have done in the last two classes. So the first thing, this was our D'Alembert's principle, and we have already derived it. Okay, let's just try to remember the terms here. Okay, the terms here are basically nothing but the first term that we have is this. Okay, the first term is FIA, which is nothing but A stands for the applied force. And we remember that the constraint force vanishes if you're basically considering generalized coordinate, right? So delta Ri refers to a virtual displacement, and we also developed the idea of virtual displacement. And this was our D'Alembert's principle. So for your exam, this will be a descriptive question. Should not be less than 5 marks. Okay, so it will vary from 5 to 8 marks. So if you do that, and I use D'Alembert's principle, so you have to start from this particular point. Don't need to derive D'Alembert's principle. Oh, okay. So you just need to write down this equation and say this is the D'Alembert's principle. Okay. So this is for an equilibrium system. So equilibrium system means the total force acting on a particular point is basically zero, right? So in general, when we go into more realistic picture, the system might not be in equilibrium. Okay. So your F is equal to ma will be valid. Or if you go by the Newton's second law, F is equal to Pi valid. Okay? We're going to use that. So the derivation starts from here, but then you have to write down what is D'Alembert's principle. Okay? So what we do here is we consider a system in motion. So see, it's a good habit that as I speak, you can keep on writing, but don't write everything on what I say, because ऐसे लिखोगे तो, as I said yesterday, पूरा किताब बन जाएगा. You cannot write so many things. So just try to understand what I'm explaining here. So if you consider a system in motion, it will definitely have some acceleration. And then if we consider acceleration, okay, okay, just wait, get the pen. So if we consider the acceleration, we know F is equal to ma, right? So if we have m into a, that means Fi minus Pi dot is equal to 0, because this F from Newton's second law is Pi dot, right? So we can just write down F is equal to Pi dot, or F minus Pi dot is equal to 0. So this is valid, right? And if we just do that, okay, we can actually obtain this relation. So where do we get this relation from? Because, you know, if you remember, okay, if you remember this, okay, the force that we have here is nothing but a combination of the applied force and the, okay, just take the pen. Okay, we do have a combination of the applied force and the forces due to the constraint. So Fa is equal to capital F minus fi, or fi is equal to fia plus fi, right? So you can just replace it here. We can just do the replacements here, because this force can be written as fi, which is the applied force plus force due to constraint, and minus p is already there. Okay, and then we can put it into the D'Alembert's principle. So what was our D'Alembert's principle? So we have that the force dot the virtual displacement is 0. So if we do that and we say that the constraint forces does not affect, so we can simply say that this part, okay, this part fi dot delta ri will become 0. So this will become 0. This is something which you have already seen before, okay? So I'm putting up the recorded lecture so that you can always go and revisit and try to understand this. So you can simply write it down as fia minus pi dot delta ri is equal to 0. This equation, when we will start analyzing, will actually lead us to the Lagrange's equation. Okay. So if you remember Lagrange's equation, d dt of del L del Qj dot minus del L del Qj is equal to 0. We've been using it a lot in the first unit, but we have not yet derived it. Okay, we're going to derive it today. So in this equation, there are two parts. See, this is the first part, and this is the second part. Okay, so there are two parts to it, and we are going to do it part by part. Okay, we are going to do it part by part. So let's do the first part. Okay, and then we are very much comfortable with all the technical terms. The first term is holonomic system. So if we basically have a holonomic system, we can actually write it down in this form. Okay. Okay. So if we have a holonomic system, we can actually write it down as a function of the different generalized coordinate and time, okay, and which is equal to 0. So what we will do is we will introduce the generalized coordinate, which is qi. Okay, and we have also seen degrees of freedom idea. So if we say that there are n particles and then there are k constraint, there are 3n minus k generalized coordinate. Okay, and then what we say is that this ri, okay, which is nothing but the position vector. Okay, this ri is the position vector, is a function of the generalized coordinate and time. Okay, so that is important. So now what we say is the velocity. So what we are going to do is we are going to actually develop a base here. Okay, so I think these things we have already done, so I'm going a bit fast. If you just write it down, I think it will be okay. I'll be just on this slide for some more time. So how can we write down the velocity now? Now, you know, if you already know the position vector and we take the time derivative of that, we are actually going to get the velocity, okay? The change of the position vector of that particular point with time. Try to understand this. This is in terms of position vector, okay? So it's basically a vectorial function. So we have got Vi is equal to, we have got Vi is equal to Ri dt is equal to Ri dot. Okay, so that is nothing but your velocity. Correct. This is your velocity. Now you know in the last class also we have seen that this Ri dot is there, but then actually we can actually differentiate with the function. Okay. So we can just simply write it down as del Ri del Qj dot plus del Ri bar del T. Okay. So you see this Ri dot actually is nothing but a function of Q1, Q2, Q3 and time. So it is actually a partial derivative. Okay, it's basically a partial derivative. Okay, so if you just take ddt of this, so you're going to take ddt of this particular function. So ddt of this. So you see, you have to use all the partial derivative term. So you have to take the summation of del ri, del q1, del r2, del q2, and so on, and keep on adding it up. Okay, so then you just take it, and then you can find it out. Okay, and then this is your relation, and I'd like you to still check this once, okay? Because I think you have done it before, but there might be a bit confusion. So sit back, relax, and try to understand it, okay? But this is actually maths, not physics. It's a part of partial derivative. If you are having a position vector, which is actually a function of, let's say, q1, q2, q3 in time, and if you want to differentiate it with respect to time, you have to consider all the coordinates, okay? And then that will become a partial derivative of that, okay? And then you take the summation. So then we have this base, this is fine. And then what is our next step? The next step is this, okay? So what we do here is this. So if we have the velocity now, which is actually a function of, let's say, qi, okay? Just wait. Yeah. So what happens here is this: when you basically have it here, qi velocity is a function of qi dot and time, okay? And we can write down the virtual displacement, okay? So we can actually write down the virtual displacement, okay, as this. Okay, just hold on. Okay, so actually I'm in a car, so I'm just moving around. Okay, so that's why there is a confusion with classes. Okay, so we'll continue here. Okay, so what we have here is we can actually write down the relation for virtual displacement now. So if you remember this, this is something which we have already done. Okay, this is already something which we have already done. And then we saw that this delta Ri dot delta Qj or delta Ri dot Qj will actually give you n cap. Okay, so can we use DLMBus principle now? Yes, we can. So what is the first term in DLMBus principle? If you remember, that was nothing but Fi bar dot delta Ri. Okay. So what we can do is we can take the summation over I and j and Fi bar dot delta Ri delta Qj dot, okay, Kronecker delta Qj. Now you see this. This is the term which actually defines the direction. So whenever we are considering the force, okay, we are considering the direction also, and that direction needs to be defined. Okay, so we are defining the direction in this delta Ri. So this is the virtual displacement. And if you don't remember this, please try to go back to the last, I think the second last lecture that we had. Okay, there actually I have explained this part. Okay, so this is already done. So okay, so this is already done. That's why I'm going a bit fast. So we can put it here in this, directly in this. Okay. So what is this term now? This term also we have seen. This was actually nothing but the generalized force. Generalized force. So you see everything is already done. And this Fi is nothing but we have dropped A because we don't want to confuse. Okay, we can write down A, no problem. This is basically an applied force, so we can write down A. But then this is the generalized force. So that means the first term in the DLMBus principle is nothing but the generalized force. Okay, so this is the first term. So we'll keep that first term aside, and now we are going to tackle the second term. So in the first term, okay, I'll just put everything on here. The first term that we have here is this, okay? And then if we just consider this Qj, which is nothing but summation of Fi del Ri del Qj, is a generalized force, just at the same slide. So this is something which you already know. What we are going to do new is with the second term. So if we just go back and check the second term, we actually know that the equation from where we are trying to derive TLMBERT's relation is summation Fi minus Pi dot delta Ri is equal to 0. So the second term is this Pi dot delta Ri. Okay. So if we use it here, can we do the derivation now? Okay. So what is P? P is equal to mass into velocity, right? So you know that P is equal to m into v. So if you take pi dot, this will be nothing but v dot, right? And v is equal to nothing but x dot. So that means or r dot in terms of the position vector. So you can just simply write it down as MIRI double dot. The momentum is MIRI double dot. Okay, and then this virtual displacement is again. So this is a form which is important, which you should remember. Okay, but then we can actually rewrite this equation. See, what happens is this. This is r double dot. So that means it is ddt of r dot. Okay. So if you can take ddt of r dot, then you have to differentiate two terms here. Okay. And that is something which you are going to do. So this MIRI double dot, we actually have one ddt, which we can differentiate with this term. Okay. This term. We have to differentiate with the second term. We'll differentiate it with the second term. So our first term is Ri dot, okay, and the second term is delta Ri delta Qj, okay. And you might say that why I'm putting this in this way, because we don't want to change the position. Okay, it's basically a product. Okay, product of two vector components. So we are not changing interchanging the position. Okay, so what we have it here is this ddt of ri dot and ddt of delta ri delta qj. So if you do that, we get this relation. You can do it on your own also. And then if you look into it mathematically, okay, there was a chapter on partial differentiation. If you look into partial differentiation, you can always interchange ddt and delta delta qj. That won't change the result. Okay? That will give you the same result. So you can always interchange this. So that means this ddt of delta ri delta qj, ddt of delta ri delta qj is equal to delta qj delta delta qj of dri dt. Okay, so you see, you can just interchange this because I said that we can interchange this and this. So I'm interchanging it here. Okay, I'm interchanging it here. Okay. So we can actually interchange this. Okay, so this is important. So if we can actually interchange this, so if we can actually interchange this, we can write down the equation in this form. So this particular equation will become this equation. Okay. So please be with me. This equation is a bit long. The derivation is also a bit long. But then you have to write it down in your copy. Try to understand. If you have any doubts, you can always come back to me. Okay. So that is important. Okay. So what we can do is, okay, I'll take all this so that it becomes a bit easy for me. Okay. So in this way, what we can write down is, how can we write down delta vi? See, delta vi delta qj dot can be written as delta ri delta qj. How? Because delta ri delta qj dot, we can write it as delta ri dot by delta qj dot. Delta ri by delta qj can be written as delta ri dot by delta qj dot. But what is delta ri dot? Delta ri dot is nothing but delta vi. Okay, so you can simply write it down as delta vi by delta qj dot. So delta vi by delta qj dot can be written as delta ri delta qj. Okay, so delta ri by delta qj and delta vi by delta qj dot are the same. So we will do what we will do it. Whatever we have, we are going to insert everything into the second term. What are the things that we are going to insert is this. Okay, so let me just go back to the previous slide, I guess. So we have this equation and we are going to change everything here. See, delta ri delta qj we have, we are going to change it. We are going to change this also. And then we are going to see what exactly are we getting. Okay, so this is what is the importance in the next slide. So we have it here. So what we will do is we will insert back in the second term. And in the second term, what we will say is that ddt of mi ri dot, that is already there. And there we actually had delta ri delta qj. In place of delta ri delta qj, we write down delta v delta qj dot. Okay. Why we are doing this? Because Lagrangian, I told you, it's kinetic energy minus potential energy. So we must include a term for kinetic energy. So we are including velocity here. We are slowly arriving at the result. Okay. And here we are going to write down this. We'll interchange this. So please look into it again and again so that this becomes clear. Okay. Now this MIRI dot delta VI delta QJ dot can be written as half of MI VI square into delta delta QJ dot. How? Because when we differentiate this, delta delta qj dot of half mi vi square. How do you differentiate it? You can just simply take half mi outside. Okay. And then we can take del del qj dot of vi square. So del del qj dot of vi square would be nothing but 2 times vi, okay, into or vi into delta vi delta qj, delta v delta qj. Okay, so we can cancel this too, and then we get mi vi delta v delta q. So that is mi vi means ri dot delta v delta qj. So we can always write it down in this form. Similarly here also we can actually write it down in this form. Okay, we're just playing around so that we get the kinetic energy term. See, we got kinetic energy here, we got kinetic energy here. That was the aim. Okay, so now what happens is we will go to the kinetic energy. So you see kinetic energy is half mi vi square. So we can replace it. So if we replace it, see, this equation becomes such a simple equation. Okay, it becomes ddt of delta t delta qj dot as delta t delta qj. Okay, so this is our second term. What was our first term? the generalized source. We are going to combine them together. Okay. So what we do is this. So we will combine the first term and we'll combine the second term. Okay. And then if you recall this, this was our second term, which we have just now derived. And the first term we actually derived was nothing but the generalized force. Okay. And then both of them had the virtual displacement with them. So we'll take the virtual displacement is equal to 0. So this is a form of the equation that we got. That means we are slowly arriving at the result. Okay. In the next part, what will happen is this. So let's say this delta qj's are independent. So if delta qj's are independent, then each term has to be 0. What do I mean by this? It means that if delta qj and this are independent, okay. So so if we just take this part and this part independent of each other, that means this part separately should be 0. Okay, this is a virtual displacement, so this part separately should be 0, so that the answer is 0. So if you do that, what we see is this part is 0, so that means ddt of delta t delta qj dot minus delta t delta qj is capital Qj, which is the generalized force. Okay, so does it represent a holonomic system? Yes, because it is written in the form of an equation now. Okay, so this is basically a second order differential equation. You see, it's a second order differential equation. What we will do now is we will basically consider a conservative system. Okay, we will basically consider a conservative system. Sorry. So if you consider a conservative system, and we know that for a conservative system, the work done, okay, doesn't depends only on the start and the end, and it does not depend on the path that it follows. Okay, and if you remember the ideas that you had developed for between force and potential from your class 12 onwards, force is directly related with potential. Okay, so we can simply write it down as nothing but minus delta of v. Okay, so this is what is the conservative system is all about. So can we use this relation? Yes, we can. So we'll just try to use it, plug in it here. Okay, so if we use this, we can write down the generalized force. We already have the generalized force q is equal to fi into dot delta ri delta qj, already have it. We'll just replace this f by minus of delta iv. So it is done very intelligently because we have a force term, we need a potential term, so we can simply just replace the relation. Okay, so we can just simply write it down as minus delta I into v. Okay, delta ri delta qj. So now why does this happen? Why do we get minus delta v by delta qj? Because you see this term. Okay, this is something which is done here. Minus delta v delta I into v. You know this gradient and all that you have done. Okay, in your mathematical physics in the matrix form. Delta is equal to I delta x plus j delta y plus k delta x and so on. Okay, so those concepts are still valid here. So we're just differentiating it with respect to r. Okay, so we're just taking it delta vi as del ri of v, and then this is there, and so this delta ri gets cancelled. We get minus delta v delta qj. So that means this function, which is the generalized force, is minus delta v by delta qj. Okay, so then you see we have already done a lot of things. We are going to just replace it here. See, we already have a term here qj. We are going to replace it. Okay, so let's replace now. Let's see what happens after replacing. So after we replace it, okay, after we replace it, what happens is this. So you have this term, and then you take it on this side, and then this term is this. This term is this. So ddt of delta t delta qj dot remains the same, minus you can take within bracket, this term is here. Okay, and this minus qj is nothing but minus delta v delta qj. Okay, and you can take the common minus, then there will be a plus, and then there is already a minus in the final answer. So this is 0. You can just replace it, and then you can see that this is del qj, this is also del qj. So you can just take t minus v here. So t minus v. Okay. So this is del t minus v delta qj is equal to 0. And what is t minus v? T minus v is nothing but L, the Lagrangian. Okay. The Lagrangian is basically the difference between the kinetic energy and the potential energy. So this will give you the equation of motion. So what we get is this. Okay. But then before that, we can do something additional here. What happens is when we basically consider potential as a function of this generalized coordinate, okay, we have seen in our previous classes that this potential is not a function of the generalized velocity. So that means delta V delta Qj dot will be 0. So that means this uh, what we have is ddt of del of t minus v divided by delta of qj dot minus del qj of t minus v is equal to 0, right? So we this term we already got now, we got it now, but this term can be written in this form. Why? Because this term was delta t delta qj dot. If we put a minus v, there is an additional term, but we know that delta v delta qj dot is 0. So we can put it here, because if we just expand it, this is anyway going to be delta t delta qj dot, going to remain the same. So we'll just introduce L is equal to T minus V, okay? And we know that the total energy is T minus V. So we can just simply write it down as ddt of delta Qj, delta L delta Qj dot minus delta L delta Qj is equal to 0. This is your Lagrangian, okay? This is the Lagrange's equation.